I am really thrilled to be speaking to you all today about tackling questions in chemistry with quantum computers. First and foremost, I wanted to introduce chemistry research using Qiskit. So there's all sorts of capabilities that we have. If you go to qiskit.org, you can check them out for yourself. We have some new modules using and looking at things in applications, different types of industrial use cases, algorithms, characterization. We have our circuits and all sorts of extensions. So I really, off the bat, say, go check it out. You don't have to know anything besides Python, and we have some tutorials and Jupyter notebooks online that then you can try your hand at. And this will give you a sense of what we do when we're actually looking at researching chemistry topics. We also, use Qiskit, and we use it to access and run different calculations on different backends and on different devices, different quantum computers with numbers of qubits and different quantum volumes. So it's a really exciting time to be a part of this research as everything's coming up and together all at the same time, the software, theory, and the hardware. So what do we do when we think about simulating a molecule and thinking about it for chemistry? So, on the left side of the screen, I show a molecule that's near and dear to many of us, myself included. Every morning, need my caffeine, right? And then what can we do on the actual quantum hardware to gain some interesting insights about the nature of the molecule, how it behaves, how we might expect it to react, for example, what kind of spectral properties it might have, that kind of thing, that are very interesting to chemists to understand. And bottom line, we do a lot of work. There's a lot of mathematics behind the scenes to understand how a chemistry molecule, for example, behaves. So effectively, what we want to look at is our second quantized fermionic Hamiltonian, and look at it in terms of the basis set method. We then, in order to be able to actually take the molecule and map it onto the qubits, we have to transform this into effectively a quantum Hamiltonian, so something that contains Pauli terms. And what this allows us to do is effectively have one spin orbital per qubit as a way to understand things like, for example, the ground state energy of a molecule with a certain number of electrons in it. So this is the workflow. This is effectively what we're looking at when we convert it into the qubit operator in the software itself. And then in addition to that, we've been able to look at new areas as well, such as n-body integrals, bosonic operators as well, to be able to more accurately identify and describe a given molecule of interest. So with that, we've been able to expand this and use these chemistry and materials modules to start looking at things that are of importance to chemists today. So thinking back to 2017, which, by the way, that is when I personally got the most excited about what we were doing in the chemistry space with quantum computers. In 2017, published a paper where we looked at the ground state energy and the dissociation curve of lithium hydride. So effectively looking at how the energy changes as you move the lithium and the hydride apart from each other. In 2019, as was shown here on the left, we were able to apply error mitigation techniques in order to get the actual value, the exact value, and the value that we were calculating with our quantum computer to closer match, and saw a 10-fold improvement. So we utilize all sorts of methods like this that we're developing and that are coming up in the theory and applying it then to real-time calculations of interest for things like ground state energies for molecules. The other thing that's important to note about this So lithium hydride, if you look at in the, in the lower of the two panels in that left panel, you can see that at around 2.5 angstroms or so, you get this bump in deviation away from the real or exact value, which is the pink line. And that's kind of interesting because if you apply your chemical intuition, and if a chemist looks at that and applies their chemical intuition to what that meaning is, you can think about it as trying to describe a very complicated part of the dissociation curve, where in lithium hydride, you have something that is going from more of an ionic type of dissociation mechanism, where you have a plus and a minus charge, to something that is more biradical in nature. So where you have like a neutral hydrogen atom and a neutral lithium atom. And so you can imagine that that can be a very difficult part of the dissociation curve to explain. So what we found is that indeed what we need is a higher circuit depth for that particular calculation. And this is something that we are continuously to work on and improve as we get better and better devices with higher and higher fidelities. We are able to start looking at more complex circuits, or circuits that have high circuit depths, to be able to start thinking about how we might address some of these challenges. In addition to that, we've looked at all sorts of different properties. We think it's really important to think about things such as the ground state energy, but also other properties of molecules that chemists might care about, such as molecular excited states, chemical reactivity, and dipole moments. Again, how do you explain the charge and electron density distribution across a molecule? So we'd want to look at something like a dipole moment, which is a little bit more complex. We'll talk a bit more. I'm going to go in depth a little bit on some of the reaction coordinate work that we did with Mitsubishi Chemical, and as well as researchers in Tokyo, our IBM site in Tokyo, and also Keio University. And so what we chose to look at in this particular instance was part of how a lithium metal reacts with oxygen gas to create a battery and an energy storage device. So what we were evaluating here was the change over looking at a caged lithium superoxide dimer, which is a part of the chemical reaction, as it goes from the cage structure to something more linear. And so we weren't having to evaluate bonds breaking and forming between different molecules, but rather a rearrangement of the molecule itself. And this is a very nice example of something that is small in size, meaning that it doesn't have too many spin orbitals, so that we can model it on our quantum computer, but yet having, a real tangible use case and having real value if we were able to derive and understand, how the mechanism of lithium peroxide forms within the battery. That could lead us to be able to understand engineering or chemistry changes for the battery itself to get it to a place where it could be actualized. And it, holds the promise of having a much higher energy density. So you can think of a car that drives 500 miles, for example, using a lithium air battery in the future. It looks easy on paper. It's much more complicated, as you can imagine. So this, again, is what we were looking at, is the rearrangement of this reactant, transition state, and product as we evaluated the reaction coordinate. And here are our results. So what we first did was model the exact energy values and classically compute that using full CI calculations. And then we were able to look at it using a simulator first to get an idea of how the RY ansatz would work on the quantum computer. We then looked at running the calculations for these energy levels on the actual hardware, and found that in all cases, it actually overestimated the energy value by varying amounts. And then when we applied that error mitigation that we saw back in 2019 for lithium hydride, we were able to get much closer to the exact values. And in some cases, they pretty much were directly right on top of each other. So this is really good efforts and work towards research towards starting to think about, that dotted line, starting to show that transformation as you go from reactant to product and map out along the energy pathway. So it's step towards starting to think about using quantum computers for reaction mechanisms. And with that, I want to talk to Couch at Mitsubishi Chemical about some of our continuing ongoing work, starting with this and where do we go in the future. I'm really excited to talk to Couch today, who is our principal scientist at Mitsubishi Chemical. He is also the team lead in quantum computing there. And he's been one of our great collaborators that we've gotten an opportunity to work with through the KO Hub on some of these quantum computing problems. So thanks for talking to me today, Couch.
Thank you. I'm very glad to join this meeting.
All right, so I have a ton of questions for you about how you think about quantum computing for your business use cases and how we do research. So one question I have, how do you pick your chemistry problems that you want to look at on a quantum computer? So like our lithium air paper that we published on Archive, like how do you pick these problems?
Okay, and from industry side, currently we are using density function theory for material design. And however, the density function and theory is not very accurate for some particular materials. So we pick some real world problem which is difficult for density function theory to quantify. And we pick up the lithium air battery because this problem, this material's energy level is very degeneracy. So it's very difficult for a DFT. And also we pick some problem for the excited state calculation. This is also a very hard problem issue for the DFT method. So we want to use quantum computing, which DFT problem is difficult, which is difficult for DFT method, and we pick such cases. Yes.
So if I can restate, so you pick problems that are difficult for today's, classical methods of computation.
Yes.
But at the same time, they're of interest to you, right?
Yes.
So I'm curious, what insights do you get from these studies, and how do you use those insights that you glean from the work that we do together?
And we obtain the insight is to whether the quantum calculation on current quantum computer can give us accurate result, which is helpful for us to design materials. And we find first the quantum algorithm is a very high-level calculation method. But one problem is the error mitigation, the noise from the quantum computing. So the most insight from our collaboration is that we think we need to combine the quantum algorithm and error mitigation algorithm so that we can utilize the current quantum computing for real-world problems.
Yeah, absolutely. So really leveraging the tools as they become available and then applying them to the problems that we're looking at together.
Yes.
Having worked with you on a couple of projects, right? Like one of the things that I've noticed is that things, always you get into it and you come at it with I'm going to research this problem, and there's lots of innovation that happens along the way and surprises, right? Little insights that we glean as a part of just, studying these chemical reactions, for example, on the hardware and making that leap from, the simulator to the hardware, right? Like that in and of itself can always be it can be a challenge. It can be, really interesting to try to fine tune and figure out which the best circuit is, right?
Yes.
So I'm curious, like, has that been your experience as well? Like, what insights do you think we've gotten or surprises along the way when we are testing this on real hardware?
Yes. Thank you so much. And I think before I run the calculation on hardware, and most algorithm use give us a very accurate calculations. However, when we apply this on the hardware, because the noise, the result is not very good. And this is something can give us which algorithm is appropriate for us to run on the hardware, and how to improve this algorithm so that we can give a satisfied result. So I'm very and to me, I'm very happy to have some algorithm provided by the IBM, such as the heuristic ansatz and some error mitigation method. And this is very important for doing calculation on the real hardware. And we get the insights from these calculations.
Yeah, I totally agree. And I think we've, as a result, we've found some really interesting, results and as a part of our research and just going through this exploration at all. So my last question is just, how do you, think about what type of skills people need to be able to do research like ours?
Okay, and ideally, if a person have skills of quantum and chemical calculation, quantum physics calculation, and control the hardware, it can give us a very helpful result. But practically, I think this is impossible for have such ideal people. So I think that we need to have a team which have different background from this, which has these different useful skills. So I think not only the person which is important, but also the people which has different background is also important to do the right things. Yes.
I completely agree. And I think that this is another reason why, like, being a part of a global community, right, with people coming with all types of backgrounds and areas of expertise coming together to solve problems is really like necessary to be able to advance science.
Yeah, absolutely. Yes.
Awesome. Well, thank you so much, Couch, for talking to me today. This has been a great conversation, and I'm looking forward to the rest of the conference.
It's welcome. I'm very happy to talk with you too. Thank you.
Thank you.